Hi, everyone, and welcome to today's lesson. Today we're going to be talking about eclipses, right? Eclipses with the moon and everything. So, the question of the day, right? How does the position of the Earth, the moon, and the sun create an eclipse? Kind of like this is a time lapse picture going on right here of a lunar eclipse actually happening, right? And so that's what we need to get into today. What happens is it's the position, it's how the Earth, the moon, and the sun, those three things, how they're lined up. Well, that's what's going to cause either what's called a lunar eclipse or a solar eclipse, right? And so, yeah, that's how they align. So that's what we're going to get into. Hey, first, kind of a fun fact for you. Did you know that the moon is actually moving further away from Earth every day? You know, the moon, it turns out, is a little bit further away today from Earth than it was yesterday, and it'll keep doing that, right? Over time, it'll slowly get further away and further away, and eventually it'll get so far away that you can imagine, like, generations from now, when they look up at the moon, instead of it being, the size that it is now, it'll be much, much smaller, right? Or if you rewind way, way, way back in time, I mean, when they saw the moon, it was significantly closer than it is today and everything, right? But eventually, right, you're going to see the moon, and imagine if you're the person watching the moon, and all of a sudden, like, it's so far away that there's not enough gravity from Earth to hold on to it anymore, and it just kind of like goes away off into space. Like, imagine watching that, being like, there it goes. You know what I mean? Like, it'll be kind of sad because that really will probably be pretty much the end of life on Earth, or at least the way we know it, because the moon actually holds Earth um, at its tilt that we have to the sun. So without the moon, our planet will start actually swerving uncontrollably and everything. So like the North Pole and the South Pole, they won't necessarily always being faced away from the sun. They might rotate around. But what that means is, well, then all of that ice is going to melt and everything. Other places are going to be cold. So there won't be consistent growing seasons anymore, and it'll just be a mess. But don't worry, that's a long time away, way before any of us have to worry about it, because the moon's only moving away from Earth about the speed that your fingernail grows. Is literally about the speed that the moon is moving away from Earth. So we're good. We're good for a long time. We'll also talk, like I showed you a video earlier about how the moon got here, right? And one of the best theories that we have right now is something smashed into us, right? It basically caused Earth, think about it, basically to explode, right? And then slowly over time, it kind of recoalesced back together. And that's where we have, the Earth and, the moon kind of spinning around Earth and everything, came from something really big hitting us like a long, long time ago when the solar system was just forming. Okay, let's do a practice quiz here, right? One of the big things that you want to make sure you understand about the moon are the phases, right? So if I show you a picture like this guy, like this guy right here, right? Which one of the phases is the picture of the moon? If it's on the part that's lit up is on the right-hand side, right? And it's just a kind of little sliver, that's going to be waxing crescent. Ooh la la. Get it? Croissant. Okay, crescent. All right. How about this one right here, right? For this one, right, the side that's lit up is over on this side of the moon. It's about halfway, so it's going to be last quarter, right? Last quarter. Now, be careful when I give you like any kind of like heavy duty quiz or test or anything like that. I mean, this one you could argue is gibbous. Is it just slightly more than halfway or something like that? So, don't worry. Like any quizzes that you're going to get, if it was a gibbous one, it would be like significantly past halfway. It's kind of hard to actually get a picture where the line is exactly right down the middle. So if it's even close to being either first or last quarter, right, then just assume that's what I'm talking about, right? If it's going to be a gibbous one, it's going to be, definitely different. How about this picture? There's a picture of the moon right here. Can you see it? What would it be called? The new moon, right? Because it's basically the side that we're facing is the side that's not getting any sun right now, so it's just black. Okay, here we go again, right? This is, roughly halfway through, but this time the sun is shining on the right-hand side of it, so that means that this is going to be a first quarter, right? Remember, whatever is on the right-hand side, that's what's moving across, so this is the first side that gets lit up for it. How about this picture right here? So here's a great example. Look, there's a little bit of the moon missing over on this side, so this is what I was talking about with, right? This one's definitely not like a quarter, first or last quarter of the moon, right? It's definitely got more of it, but it's not all there, so that means it's going to be gibbous. and it's going to be waxing gibbous. It's getting bigger. You know, the lit side's over here, so it's going to be a little bit more tomorrow, a little bit more the next day, and eventually it'll be full moon really, really soon. This one right here you go. Hopefully you can get that one as full moon, right? This one right here, we've got just a tiny little sliver of the moon over on the right-hand side, so that's going to be waxing crescent. Ooh la la. Remember that. Over here, now this one, now look, it's almost full moon, but there's just a little bit missing over on this side, so that means it's going to be waning gibbous. So this would happen right after full moon. It's going to start waning away. And then this one over here, now you've got a little bit of the crescent way over on the left-hand side. So that one's going to be waning crescent, right? It's waning away. Okay, and that kind of gets us to through the different phases of the moon. That brings us to the question, why is it that the cow wants to go to space? Because it wants to see the moon. Okay, that was bad. But anyway, I thought it was kind of funny, right? Let's see here. So what we want to get into, the meat and potatoes of today, is solar versus lunar eclipses. Right now, what you want to understand so you don't get the two of them confused is whatever the name's implying, right? There's solar or there's lunar. It's implying whatever's disappearing. So if you say solar eclipse, right, it seems from our perspective that the sun's disappearing because of the moon. If you're talking about a lunar eclipse, then it's just kind of like assuming, again, from our position, it looks like the moon is disappearing away, right? So that's kind of the difference between the two of them. It's whatever looks like is going away. That's what the name is implying between the two of those. So let's start with the lunar eclipses because these happen more frequently that we get to see them and everything, right? And so here's an actual picture of a lunar eclipse. It's not necessarily that the moon totally goes completely black and you can't see it. It just gets really, really dark red because Earth's shadow is on it when it should be, kind of full looking and everything. So it's kind of like the picture that's going on here. So here's the setup. You've got the sun over here, Earth is in the middle, and the moon, right? The moon normally, as it kind of orbits around the planet, normally you got to imagine like the Earth is always casting a shadow out into space, right? But normally the moon, as it crosses over this little line right here, it's either like above it, it's up high, or it's down low below that. But every now and then as it's spinning around, they all just kind of line up perfectly so the moon actually goes through that shadow, and that's when you have a lunar eclipse going on right there. So here's an actual photograph of that happening, right? The lunar eclipses, this is one of the best proofs that we had long, long ago that Earth was round, right? Back when people thought it was flat and like a flat slab. Well, when, our shadow gets cast on the moon, it was definitely had a curve to it and everything. So you could actually see, how big, the Earth was, and you could actually see, the shape of it and everything, right? Let me show you here is a quick video of a lunar eclipse happening. Just greatly speed it up. Normally this takes like a couple hours. But here you go. You've got a picture of the full moon, and here comes Earth's shadow. If you could see it in person, it would look more like, hold on, the camera corrects in a minute here. Earth's shadow cast covers and covers. There you go. It would look really more like this, right? The black part was just the camera trying to correct for it. And then as Earth's shadow moves away, then it kind of like starts revealing more of the moon again. And those are some clouds passing overhead. Right, so that's a picture of or a video of the actual lunar eclipse happening, and they happen a couple times a year, depending where you are on the planet. Depends if you can see it or not. Which side of the planet you're on and everything. But so they're not like common, like they happen all the time, but they're not super rare for it either. But what is more rare are the solar eclipses, especially if it's a full solar eclipse that happens. Right, so this is where basically the moon is the thing that gets in the middle, right? For the lunar eclipse, Earth is in the middle. For solar eclipses, the moon's the thing that gets stuck in the middle between the two of them for it. So here's the picture where you've got the sun going on right here, the moon's the guy in the middle, and then Earth is right here. And you can see while if it's switched around, so it's a lunar eclipse, we're on Earth. If you look at the moon, you can see the eclipse happening from all over that side of the planet. Right, but for solar eclipses, they're much more specific. Not only do you have to be on the right side of the planet when it happens, you've actually got to be in the right spot, right? And so that's why it's fairly rare that we see a solar eclipse because you've got to be at the right place at the right time during the right alignment and everything. So for these, they're only every so many years, if not decades, and everything, right? For them, so they're much more rare to happen. And then here's again a time lapse of one of these happening. And yeah, let me show you. Here's a video of solar eclipse actually happening right here. Yeah, this one has the dramatic music. So here you go. If you're on Earth and you happen to be in the right place at the right time during the right alignment, the moon is moving in to cover the sun. You get the diamond ring effect right there. You get totality where it's perfectly covered up. You can just see like little solar flares and things like that. Then you get the diamond ring effect again. And finally, then, yes, then it comes back around, right, where now it's moving away. You can even see some of the sunspots and stuff. All right, so there you have it. There is the solar eclipse happening. You've got to be careful. The solar eclipse, because you're staring at the sun, can hurt you. That's why you get those special glasses. Whereas if it's a lunar eclipse, I mean, you can look at the moon all you want. It's not going to hurt you or anything for that. So you've got to be careful when you're watching the solar eclipse, particularly because during totality, when the moon covers up the sun, right, then really briefly, you can take off your glasses and look at the sun with your bare eyes and everything. But you got to be careful because as soon as then the moon doesn't cover again and everything, that's where then that light can come in and that can really hurt your eyes and everything. So you got to be careful with that. Now, one cool fact is it's just a coincidence for us, right? The moon is relatively small compared to Earth and the sun. The sun is humongous compared to Earth and the moon, right? But because the sun's so far away, the moon just happens to be the same or appear to be the same size. So even though the sun's super big, when the moon comes in front of it, it covers it up almost perfectly, kind of like in this picture right here. It's just because the moon is so close to us. It's kind of like, if you hold your hand out in front of you and you move it closer and closer and closer, that your finger seems like it's getting bigger and bigger and bigger, right? Well, that's what's going on with this. And it's just kind of a cool coincidence that, the moon happens to be almost exactly the same size in the sky as the sun is and everything. It produces really nice, effects and everything like that. As the moon gets further and further away, remember we were talking about that, eventually generations from now, when there is a solar eclipse, it won't be quite as spectacular because they'll have, kind of like in the picture right here, they'll still see some of the sun all the way around. And so you won't get to see, the outer edges of the sun kind of flaring out like in the picture right here. It won't be as spectacular. So it's kind of cool that we're at the right time at the right place. Oh, yeah, here you go. Here are some of those solar picture glasses and everything for it. So remember, the difference, right? The name implies what's being blocked. So if it's a solar eclipse, the moon is blocking the sun. If it's a lunar eclipse, the earth is blocking the moon, right? Whatever the name is, solar or lunar, that's what appears like it's being going away and everything for it. Okay, so the last thing is, let me show you a video here, kind of that describes this process, but it kind of has better graphics than I can show for you and everything. See if I can.
We humans of planet Earth benefit from a great coincidence. It's a coincidence of time and of space and of math. The coincidence is this: the sun is about 400 times wider than the moon, and it's also, on average, about 400 times farther away than the moon. The apparent size of an object in the sky depends on how big it is and how far away it is. So these numbers being equal means the sun and the moon appear to be about the same size in the sky. And that's where another interesting thing comes in. Sometimes the moon passes directly between the Earth and the sun. Doesn't happen all that often, but when it does, you get magic. Or even better, you get science. You get an eclipse. An eclipse is a generic term in astronomy for when one object passes into the shadow of another object, darkening or blocking it. A solar eclipse is when the moon blocks the sun, casting a shadow on the Earth. And a lunar eclipse is when the Earth blocks the sun, casting a shadow on the moon. But how do they work? Well, the moon orbits the Earth once per month, and the Earth orbits the sun once per year. If the moon's orbit were perfectly aligned with the Earth's, essentially sharing the same plane, we get a solar eclipse every new moon and a lunar eclipse every full moon. But we don't. That's because the moon's orbit is tilted with respect to the Earth's by about 5 degrees. What that means is that at new moon, the moon can be as much as 5 degrees away from the sun, passing above or below the sun in the sky, thereby missing it from our perspective. But sometimes the moon is in the right place at the right time, and at new moon, it lies perfectly in line between the sun and the Earth. And when that happens, we get a solar eclipse. This geometry happens at least twice per year, and sometimes as much as 5 times per year. What's happening physically in space is that the moon is casting a long shadow. Usually that shadow misses the Earth, but during an eclipse, the moon's shadow falls on the Earth's surface. In fact, there are 2 shadows from the moon, one inside the other. One is a narrow cone tapering to a point away from the moon. If you were anywhere physically inside this cone, the moon appears big enough to completely block the sun. That means the shadow is very dark, and we call it the umbra, which is Latin for, you guessed it, shadow. Outside of this deep umbral shadow is a wider conical region where, if you're in it, the sun is only partially blocked. You can still see some of the sun past the moon. You're getting less light, and so you're technically shadowed, but it's not quite as dark as the umbra. This region is called the penumbra, pen in this case for Latin meaning almost or nearly. When the umbra touches the Earth, we get a total solar eclipse. But what does that look like from the ground? You don't get a total solar eclipse right away. First, the edge of the moon slips in front of the sun, and we see a little dip in the sun's limb, its edge as seen from the Earth. That's the start of the penumbra sweeping over you. As the moon slowly moves, that dip grows, becoming a bite. The sun becomes a thick crescent, then a thin one. As the sun becomes an ever thinner crescent, the sky begins to darken. Then, finally, the moon's black disk completely covers the sun. The umbra sweeps over your location, and at that moment, totality begins. You might think that this just means the sky gets dark and it's like night outside for a while. But a total eclipse is far more than that, and that's because of the sun's corona. As I'll cover in more detail in a future episode, the corona is the sun's atmosphere, an ethereally thin envelope of gas that stretches from the sun's surface into space for millions of kilometers. It's really faint and therefore usually completely overwhelmed by the intensely bright light from the sun. But when the moon blocks the sun's face, the corona becomes visible. It surrounds the sun, filaments and tendrils extending into the sky, an incredibly beautiful sight. I know many people who have said it's the most spectacular thing they have ever seen. And there's more. The moon's edge isn't smooth. There are craters and other depressions. Craters right at the moon's edge allow sunlight to stream past. We see these as bright patches around the eclipsed sun, which are called Baily's beads, because they were first described by English astronomer Francis Baily in 1836. Because the moon and sun are very nearly the same apparent size, totality is brief. The longest it can last is only about 7 or 8 minutes. That's how long it takes the umbra to move over one spot on the Earth. When totality ends and the moon starts to move off of the sun's face, for a moment, just a single spot of the sun is unblocked, glowing fiercely on one side of the moon. Sometimes you can get a circle of light around the moon's surface, and together with the bright spot, it looks like a celestial wedding ring. In fact, this is called the diamond ring effect. Then, inexorably, the moon pulls away from the sun, and the order of events is reversed. The umbra is gone, but you're still in the penumbral shadow. The sun shows a thin crescent, then a thick one, then a dip in its side, and then it's all over. The umbral shadow of the moon is pretty small where it hits the Earth, so a total eclipse is a local event. If you're too far north and south, you don't get a total eclipse, you only get a partial one, which is still cool, but lacks the mystique of a total eclipse. Remember, too, that the moon's orbit around the Earth is an ellipse. That means sometimes it's closer to the Earth and sometimes farther. If a solar eclipse happens when the moon is at the far end of its orbit, it can actually be smaller than the sun in the sky. It doesn't block the entire face of the sun, and it leaves a ring of light around the black circle of the moon. The technical name for this shape is annulus, so this event is called an annular eclipse. A lot of people think if you look at a total solar eclipse, you can go permanently and completely blind. That's really not true, but some parts of eclipse watching are more dangerous than others. I mean, obviously, it's not a good idea to stand there and stare at the sun. Looking at even the uneclipsed sun for more than a moment is painful, and that pain is the result of the damage that solar radiation is doing to your retinas. So I don't recommend it. Duh. But when viewing an eclipse, the real concern is right after totality ends. During totality, it's dark, so your pupils have dilated to let more light in. But then there's the flash of sunlight when the moon moves off, and that's intense enough to damage your retinas. That's why astronomers recommend extreme caution when viewing an eclipse, because that flash can catch you by surprise. When viewing the sun, don't just stand there and stare at it. You should always have eye protection. And make sure you have safety-approved filters. Don't try the homemade tricks you might have heard of, like looking through an old CD or DVD or using old-style camera film as a filter. These can let through too much infrared and ultraviolet light, and again can dilate your pupils, actually making things worse. Lots of companies make inexpensive filters that are great for sunspotting. We have links in the doobly-doo for more information on eye safety. Now, you don't have to worry about hurting your eyes at all when viewing a lunar eclipse, because in that case, it's the Earth that blocks the sun, and the Earth's shadow falls on the moon. So go nuts. But one big difference between the two kinds of eclipses is who can see them. A solar eclipse is localized to one spot on the Earth, or really a swath along the ground as the moon's umbral shadow sweeps across the Earth's surface. But a lunar eclipse is when the moon moves into Earth's shadow. So anyone on Earth facing the moon can see a lunar eclipse. This is why I've seen dozens of lunar eclipses, but never a total solar one. I've never been at the right place at the right time. Not that I'm bitter. The Earth has umbral and penumbral shadows too. When the moon first enters the Earth's penumbra, the dimming is so slight you hardly notice it. But as the moon moves deeper into the penumbra, it starts to darken. Sometimes it changes color, turning a deep orange or blood red. That's because the Earth is starting to block the sunlight heading toward the moon, and the only light that gets through is coming through the thickest part of our atmosphere. This blocks blue and green light, leaving only red to come through. That's why the moon and sun look red to us when they're on the horizon, rising and setting too. When you look upon the red eclipsed moon, you're seeing the light from all the sunrises and sunsets in the world hitting the moon and reflecting back to us. Finally, the moon starts to enter the Earth's umbra, and the real eclipse begins. At first, it looks like a bite is taken out of it. That curving arc is the shadow of the edge of the Earth. The moon moves deeper and deeper into the shadow until it's completely darkened. The Earth is bigger than the moon, so the Earth's umbra is much wider. While a solar eclipse is over in minutes, a total lunar eclipse can last nearly 2 hours. I once saw a lunar eclipse so deep that it took me a minute to find the moon in the sky. There's not a lot of new science you can do with a lunar eclipse, but if you know a little geometry, you can use the size and shape of the Earth's shadow on the moon to get the relative sizes of the Earth and moon. Ancient Greeks did just this and got a number that wasn't too far off. They also knew how big the Earth was using other methods, and so they had a decent estimate for the size of the moon nearly 2,000 years before the invention of the telescope. They also knew the shape of the Earth's shadow was always a circle, which only makes sense if the Earth were a sphere. If the Earth were flat, it would sometimes cast a thin shadow, but it never does. Pretty clever, those ancient Greeks. One final note. Because of tides from the Earth, which we'll learn more about in detail in a later episode, the moon is slowly moving away from the Earth by about 4 centimeters a year. As it recedes, it's slowly getting smaller in the sky. This means that eventually it will be too far away to completely cover the sun, and we won't get any more total eclipses. Do it.
All righty. So there you go. So there's a couple more examples of what's going on when we talk about, the difference between solar eclipses and lunar eclipses and everything. All right, make sure you take the quiz at the end and have a great day.